One of the things I really want to get across in these Gresham lectures is the many different ways that science happens. Sometimes, just occasionally, it happens in the way you read about in books, where somebody comes up with an idea, designs an experiment, and goes and tests it. But a lot of the time, things are more chaotic than that. I see a few nods in the audience, so clearly people agree. Sometimes science happens to us. Things occur that change our view of, in this case, the universe. And that's the story of tonight's lecture, this small object, Oumuamua, that shot through the solar system in 2017 and left us with new ideas and an awful lot of new questions as well.
The Gresham College lecture that you're listening to right now is giving you knowledge and insight from one of the world's leading academic experts. Making it takes a lot of time, but because we want to encourage a love of learning, we think it's well worth it. We never make you pay for lectures, although donations are needed. All we ask in return is this: send a link to this lecture to someone you think would benefit, and if you haven't already, click the follow or subscribe button from wherever you're listening right now. Now, let's get back to the lecture.
I did think I'd start, though, with some of the traditional form of science, the very methodical, careful work carried out, for example, by people dressed like this. This is the clean room at the Jet Propulsion Laboratory, and this is a bunch of scientists trying to work out, well, if you've ever had a problem getting a jam jar open, this is the scientific equivalent. This spacecraft, that's what it is sitting in front of them, is the OSIRIS-REx spacecraft, which journeyed to an asteroid called Bennu, which is a near-Earth asteroid. It crosses the Earth's orbit and, in fact, has the highest chance of any large asteroid that we know about of hitting us in the foreseeable future. The foreseeable future being sometime in the 22nd century. I don't think you have to worry at all until possibly the year 2080 something. So looking at most of you, we're fine for now. Even I will be long gone, I suspect. But OSIRIS-REx went to Bennu. Here it is. Here's a close-up of the asteroid. And on the right is the sampling tool that was deployed to take samples from the asteroid and bring them back to Earth. And it was designed to work on a solid surface, but as you can see in a second, as it hit the surface of this asteroid, it found basically, rather than a solid object, this body, which is a few kilometers across, turned out to be a rubble pile, essentially about as structurally sound as a sandcastle that you might have built on the beach. And this caused problems. It did indeed manage to sample lots of the material and return it to Earth. Here's the capsule sitting at the end of last year on the Utah desert, looking brilliantly like something out of science fiction. But instead of getting a few large lumps, what they got was a pile of rubble. And so there were good things about that. One of them was that even by scraping the outside of the collector, this is the outside of that jam jar, you can see that there's dust and material on the right there. They actually got 70 grams of material from the outside of the collector, which is more than they were trying to get of the asteroid in total. Some of that material's now here in London at the Natural History Museum. It's been distributed to scientists around the world who will study it. But until yesterday, they hadn't managed to get into the collector itself. There was so much material it had jammed, and they couldn't hit it against the side, or we've all done that and had things go wrong. So they had to build special tools. But I wanted to celebrate them because yesterday this happened. This is the inside, and we now have this pristine asteroid sample here on Earth. And about a third of this will be distributed to labs around the world for analysis. We want to understand Bennu's composition. We might, after all, want to divert it away from us one day. But we're also interested because it's a pristine relic of a time about 4.5 billion years ago when the planets in our solar system were forming. They may well have formed out of building blocks like this asteroid. And so as well as defending ourselves, we can learn from objects like this one. Let me take those two ideas in turn. I think having mentioned that Bennu might hit us, I should reassure you that we're actually doing okay in terms of planetary defense. In particular, There have been many ideas about how, if we saw an asteroid coming towards us, what we might do. Some of them, for example, in Hollywood films, where they suggest, for some reason, you send Bruce Willis and a team of oil executives to blow it up. That, spoiler alert, doesn't work very well. Or another film where they just send Bruce Willis. I don't know why it's always him. He's clearly a specialist. My favourite idea for years was that if you saw an asteroid coming towards you, as you could see, this material is quite dark. It's blackish, and that's quite common for near-Earth asteroids. And so my favourite suggestion is you still send Bruce Willis. We want to make sure he's still got a job. But instead of blowing it up or attaching a rocket motor, all you do is paint the asteroid white. That then changes the properties of the interaction of the asteroid and the sun. It gets a change in momentum, and if you do that early enough, the asteroid will deflect and not hit the Earth. Unfortunately, recent calculations say that you'd need to do it thousands of years ahead of any impact, and we don't have the ability to predict that far ahead. So Bruce really is out of a job. What we can do instead is brute force, and this was demonstrated a couple of years ago by a mission called DART, which brutally attacked a small asteroid called Dimorphos. Dimorphos is the thing on the right here. This is a double asteroid, and they'll be important later. It's a binary. They go around each other. The large one's called Didymos, and the small one is Dimorphos. It's a few hundred meters across. And what DART did was take a spacecraft about the size of a Mini and head directly for the smaller of the moons. And so these are images from the DART probe, which was launched to impact this small asteroid. This is really a test of technology. It's can the spacecraft steer itself accurately enough to hit this small moon? As you can see, they look rather like Bennu. It's this rubbly surface, not really solid. But DART scored an absolute bullseye. These are the last images that it sent back. As you can see, and then that's the last image that came back. We only got the top bit, and we had the strange experience of watching a mission control full of scientists who built this spacecraft celebrating wildly as their craft destroyed itself. The reason that this was done, it seems slightly odd. I mean, okay, we want to show that we can hit the thing, but the idea was also to show how much an impact like this can deflect the asteroid. That seems a bit odd. After all, I set questions for students that say, okay, we've got two snooker balls. If I hit one snooker ball with another, if you know the mass of the snooker balls, and the speed, you can calculate what's going to happen to the other snooker ball. I'm very, very good at snooker in theory. The practice I leave to others. However, because the asteroid is a rubble pile, when you hit it, it's not like a solid ball hitting another solid ball. You get material thrown up into space, and that can help you. It can have a sort of rocket effect, or it could hinder you. And actually, the impact of DART into Dimorphos was much more spectacular than anyone thought it was going to be. The team were rather reluctant for people to go out and look with back garden telescopes, but many of those who did saw the asteroid brighten. And with the Hubble Space Telescope, we got this spectacular view of a long tail of material. This is dust that's thrown up from the asteroid, streaming through the solar system over many thousands of kilometers for many months afterwards. And by studying the orbit of Dimorphos around Didymos, the larger moon, we're able to measure the deflection. And it turns out that we're pretty good at this. So if we'd seen an asteroid of this size, a few hundred meters coming towards us, and we had 10 years notice, we'd be able to launch a copy of DART and deflect it and stop it hitting us. So the question is whether we'd have 10 years notice, and I'll come back to that at the end of the talk. You can live in peril and possible doom until then. I figure that will make sure everyone listens to the rest of the talk. But I did say that these asteroids were useful not just interesting, not just because of their threat to us, but because they tell us about our origins as well. They're the building blocks from which we build planets. We've actually got quite good as well of seeing that process unfold. One place we could look to do that is actually really prominent in the night sky at the minute. So this is a beautiful picture by my friend Will Gator of the Orion constellation, which perhaps some of you recognize. You've got the 3 stars in the belt. You've got Betelgeuse or Betelgeuse at the top. And then hanging down from the belt, there is the sword of Orion. And in that sword, if you go out tonight, I'm sure it's clear. We're giving a lecture inside, so it must be clear outside. If you go out and look up, even from the middle of London, if you look at the stars in the sword, you'll see that one of them is fuzzy. It's not an actual star. And this has been long known. It's this one. It's about halfway down. This is actually the Great Orion Nebula. It's our nearest star-forming nursery. This is a spectacular Hubble Space Telescope that shows nitrogen, hydrogen, oxygen gas glowing in this stellar nursery that's about 1,500 light years away, relatively nearby in terms of the structure of the galaxy. This nebula is lit up not because the gas itself is intrinsically hot, but because it's heated by a small cluster of stars that's visible at the center of the nebula. They're called the trapezium. They're visible in a small telescope. And even through the 6-inch reflector I have in my garden, I spend ages looking at this object because you can see this three-dimensional structure, this gas wrapped around these stars that have just formed in the heart of this nebula. William Herschel, the great English observer who discovered with his sister the planet Uranus, was one of the first to write about this as a star-forming region, and he described the nebula as being composed of the chaotic material of 1,000 future suns. And I think that captures something of the drama of these objects. You've got new stars forming, their light, the winds from those stars sculpt the gas around them. That can trigger further star formation and allow stars to form out of the gas. And we learn a lot by studying these things. But we can also look very closely at the stars that are forming. This is something that the Hubble Space Telescope in particular has specialized in. And these 4 dots, this is, I'm afraid, going to be a talk about blobs. So you've had the nice images now. Just relax in, we're going to talk about blobs. At the heart of each of these dots is a newly formed star. These are stars which have just switched on, so nuclear reactions at their center have just got going. And what you can see in each of these cases is that silhouetted against the bright background of the gas in the nebula, there is a shadow, a silhouette, which is a disk of material around that star. Now, these are big disks. On average, these 4 are about 60 billion miles across, which is about 7.5 times our solar system, if you think of Neptune as the edge of the solar system, an idea we'll come back to. So that they may be big compared to our solar system, but we think these are, in fact, solar systems in the making. As well as gas in the nebula, we have dust, silicon, carbon, tiny grains, maybe 1/10 the size of sand grains. And as they get caught up in the formation of the star, they form, because of their angular momentum, into these disks. And the disks, we now know, have structure. So if we look not with the Hubble Space Telescope, but with a telescope that's tuned to the microwave region of the spectrum, to very short-wave radio, really, but what astronomers call the submillimeter or microwave, then we can see some of these disks in exquisite detail. We use that frequency because it gets us to the cool parts of the solar system. So here are 3 planet-forming disks, stars at the center. There's a zoom in on the right there, in the middle, that shows detail. But what I want you to see is that these disks have structure. They have gaps in them. They have rings. And that structure is caused by planets that are forming within the disk. So once you form a planet, it can sweep up the dust in its orbit. And so we now think all these stars are a few million years old. And so we're looking at places where planets have formed within the last few million years. Probably big planets, Jupiter-sized or more, but we're seeing their effects on the disk. I'm a particular fan of the middle one, which is a star called TW Hydri, because that first gap that you can see is 1 astronomical unit from the star. In other words, it's the same distance from the star as the Earth is from the sun. So you can imagine looking at our inner solar system 4.5 billion years ago and seeing exactly this. We can also see that this is an evolutionary process, that this forming of planets and sweeping up of dust takes time. These are a recent view, just from last year, of 20 such disks, all from this telescope called ALMA up in the high Chilean Andes. It's an amazing place and an amazing telescope, but they're arranged from youngest in the top left to oldest in the bottom right. And you can see what starts off as quite a amorphous, diffuse structure becomes a regular disk, and then those gaps appear by the time you get down to the bottom right. And so planets form after the disk. So you have the star collapse, you have the disk, and you have planets. And the fact that we can watch this happen is one of, I think, the unsung triumphs of astronomy in the last 20 years. And I don't think anyone, even those building ALMA 20 years ago, realized we were going to get this sort of grandstand view on planet formation. Now, to explain what we're seeing, we have a couple of options. One option, which is beloved by many of my colleagues, is, of course, to build a high-resolution computer simulation to take the physics that we understand of these quite complicated systems, which involve fluid dynamics and the heating of the star, plus friction between grains in the disk, plus the gravitational interaction of the newly forming planets. But we can throw all that in a very large computer, and we can build a convincing model, with music, apparently, that I don't know if we have copyright clearance for the music, so we'll stick to the image. And what you can see in this beautiful, this is a simulation, it's not an animation, but what you can see is that these gaps grow naturally, and then you start to gain some planets. And it's rather beautiful, and it's all very, very convincing. The trouble is that the simulation's cheap. There is a fundamental mystery at the heart of our understanding of planet formation, and that's going to be a key part of this evening's lecture. So let's ignore the simulation and just talk about first principles. What we're building these planets out of are things like this. This is an actual interstellar dust grain. It was captured by a spacecraft called Stardust. There was sort of a precursor to OSIRIS-REx, actually. It visited not an asteroid, but a comet. It flew through the coma, the atmosphere of Comet Wild 2, and returned to Earth with lots of nice cometary particles. But by accident, without planning, some particles got stuck on the back of the detector. Now, a few of those were comet bits that had bounced off the spacecraft and ended up there. But it was also, the back was exposed to interstellar space. And so 6 particles, I think, that were passing through the solar system happened to be captured by the detector. And they were found by a bunch of citizen scientists online in a project called Stardust at Home that spent their life looking at dust grains and looking for ones that looked unusual. The unusual ones were extracted, tested in the lab, and so this is a piece of another solar system. As you can see, it's pretty small. There's a scale bar at the top, and it's this irregular structure. And the reason it looks like this is that it started life as a bunch of little spherical grains, again, think sand grains, and when they collide in a disk like those we see around these young stars, they stick together. And they stick together because of chemical reactions, but also because they often, in the outer bits of the solar system, have ice, water ice, or carbon monoxide ice surrounding them. And you get 2 nice icy grains, you stick them together. My friend Helen Fraser does this in zero gravity on a plane that does this, so she gets a few minutes each time to try and stick dust grains together. I think I've probably underestimated or not explained the complexity of her experiment, but that's fundamentally what she's doing. And this works. And so over time, what's happening in those disks is you're slowly sticking together bigger and bigger things until you go from dust grains to aggregates like this one to maybe as much as a pebble. And then if you start sticking pebbles together, they're moving together, that can happen between the friction, then you end up with things maybe the size of a boulder. So I have my own simulation of this process for you, which I think is as high-tech as the previous one. So this is a bowl of water. It's being stirred to simulate the disk. So this is the rotating disk. And then we're going to introduce some grains, in this case of pepper, into the bowl. And this will be utterly unspectacular because initially you won't see the pepper, but as it rotates, friction brings them together, the pepper grains start sticking together, and they become visible in the video because they've grown. So this is exactly the same process. I'm not saying planets are made of pepper, but you get the idea. So this works fine until you get to boulders. And the trouble is, once you go from here to a boulder, When I collide two boulders together, I don't get a bigger boulder. I get rubble. I go backwards. I get smaller things. And so this is a problem. I've broken the chain of getting larger and larger and growing towards the planet. Now, once I get to things roughly the size of, I don't know, one of the buildings around us here in the city, when I collide two skyscraper-sized things together, I get rubble, but I get a lot of it, and gravity can pull that back together. So once you get to big things and they collide, gravity is important. And so we can grow from skyscrapers to planets. We understand how that happens, and we can go from dust grains to boulders, but we don't know how to quickly jump that gap in the middle. As long as you let me click my fingers and cross that gap, I know how to form planets. But there's this fundamental problem in the middle. And that's the problem that I think a solution may have appeared in our solar system. We weren't looking for it. This wasn't the result of a targeted search for a solution to this problem, nor was it particularly a targeted search for objects like the one I'm going to talk about. The discovery was made by telescopes in these two small domes, which are in an observatory on top of the Hawaiian island of Maui. It's an experiment called Pan-STARRS, which is funded by a consortium of academic institutions and the US Air Force to look for threatening near-Earth asteroids. So the fact that we know that there's nothing more threatening than Bennu that's large and heading our way is primarily due to Pan-STARRS and surveys like it. What they do is they scan the whole sky and they look for moving objects. And in October 2017, they found such an object. These are images from the 19th of October. On the left, the red lines, by the way, are areas where there's no data available. The US Air Force, having funded this mission, realized that if you're looking for moving objects in the sky, you also find things the US Air Force doesn't want you to find. And so they remove bits of the sky from our data to hide what they're doing. And then they have to remove bits of the sky that don't hide what they're doing, because otherwise, so the red lines are just that. But I don't know if you can see in the red circle, which I added, it would be really nice if the Air Force would circle the things we're looking for, but we haven't got there yet. There's a very faint smudge. It's a little line, and that's a moving object. It seemed unusual. It was followed up by a larger telescope on the neighboring big island of Hawaii, on Mauna Kea by CFHT, the Canada-France-Hawaii telescope. And that image is much clearer on the right. Now, this time they're moving the telescope to follow whatever this new object is. So the dot is the new object. The lines here are stars that move relative to the thing. So we know it's moving relative to the stars. In the bottom, there's also a close-up image. And all it really tells you is that this is a point-like source. It's not a big thing. It's not a comet at this stage with a tail. It's just a dot in the sky. And at this point, most people are thinking this is, in fact, an interloper from the outer solar system. So our familiar model of the solar system with the planets, with Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, that's just the inner bit of our solar system. Most objects in the solar system live out in what's called the Oort cloud, which is about a third of the way to the nearest star. And this is the vast reservoir of icy bodies left over from when the solar system was forming, that feeds into our store of comets that we see, icy bodies that come into the inner solar system. So people are thinking this is a comet, and they began to plot its trajectory. And it was immediately unusual. So there's the solar system. The dotted line shows the path on which this object traveled. It came down from up in the north, came rapidly into the solar system, slingshotted around the sun, and by the time it was discovered, was already heading off into the distant galaxy, back into deep space. And we found it after it had been through the inner solar system. There's an animated version here. It's got a few other objects in, but it's this red line coming in here, and there's the slingshot, and then it heads off out into deep space. And this trajectory was unusual enough that it was realized that this was the first interstellar object, the first large object bigger than a dust grain that we'd seen coming from another solar system, or at least from beyond ours. And so the question at the beginning about the name, well, it was originally classified as an asteroid, then it was decided it was a comet, and eventually they gave it the designation, the International Astronomical Union gave it the designation 1I, the first interstellar object, and the name Oumuamua. Now it's a Hawaiian name because it was discovered in a Hawaiian observatory. In Hawaiian, emphasis comes from repetition. So mua means far away, so Muamua is really far away, and Oumuamua is a scout. So it's the scout from really, really far away, which is rather nice. And I'm now going to show you, and I want you to be impressed, please. This is lecture 3, so I know at least some of you are up for this. This is the best image that we have of this object that I'm basing an entire lecture on. Ready? Try to contain yourselves. It's the thing in the blue circle, and I added the circle. We never saw it as more than a dot, sadly. This is an image from the Very Large Telescope, one of the most powerful instruments we have, hence the name. Again, tracking the object so that the stars blur in the background. But we never saw it as more than a dot. And so it became a bit of a challenge. What can astronomers learn about an object if all we see is a dot? Well, the first thing we can do is we can say, this is the kind of astronomy I like. We ask simple questions. We know it came from beyond the solar system because we've seen how it is moving. We can say, what color is it? And it turns out it's slightly reddish. And that's typical of stuff in the outer solar system. So you could compare this with, I know, Charon, one of the moons of Pluto, or perhaps some of the objects in the Kuiper belt, the rubble that shares an orbit with Pluto. It wouldn't look out of place. And so that means it's probably icy, and it's probably spent a lot of time in deep space, or at least formed whichever solar system it came from, on the outer edges of its solar system. You could swap it there, so that makes sense. The other thing that we can do, if we've measured colour, and we've seen it's a dot, we can keep looking at it. And it was followed for a few months, and it actually showed remarkable variation in brightness. So each dot here is a measure of brightness. When it's high up, it's bright. When it's low down, it's faint. And this is from a whole cluster of the world's most powerful telescopes. But you can see there's this pattern where it goes up and down in brightness, and then it goes up quickly and then down. But it's not a regular pattern. It's not of simple periodic relationship. And so the changes in brightness are quite big. It's about a factor of 10. Between its brightest and its faintest. It caused havoc. We're trying to plan to observe it. So we've got this unknown object that's changing brightness wildly. And so the astronomers who did this had to be really on it. And very quickly, there were 2 hypotheses about what's causing this change in brightness. And they're illustrated. And normally, for these lectures, I've been trying to make my own slides because I want to give you the most original and interesting content, but I had to borrow this next one. This is an illustration by my friend Luke Dones about the 2 reasons why Oumuamua might have been changing in brightness. And he's using a local object to stand in for Oumuamua. So the 2 options are on the right. You have structure on the surface. We could have coloured patches. We could have dark patches and light patches. And so if you imagine the cat rotating, the brightness of the cat would change over time. I'm told by Luke he tried to make the cat do this, but apparently difficult to coordinate. So that's possible. You can imagine inventing a pattern that would match what we've seen, but if you look in our solar system, with one honourable exception, Saturn's moon Iapetus, which is half dark and half white, we don't see on small bodies, and we know that Oumuamua is small because it's a dot, on small bodies, we don't see variations in colour, really. They tend to be pretty monochrome. So this is possible, but unlikely. In the other example, we have a stretched object. And if you have a stretched object, and this was the press release image that you will have seen perhaps as the most common visualization of Oumuamua. If you have a long object, then its brightness depends very much on whether you're looking edge on or side on. So this will look very different from this, if that makes any sense. And if it's rotating, then you get a change over time. And in fact, it's not just rotating, it's tumbling. So it's not just it's going end over end, but twisting as it does so. And if you model that, you can reproduce the light curve pretty well. Now, the original estimates were that this thing must be 400 meters long, 10 times, or maybe even as 20 times as long as it is wide. So it's this really extreme sort of cigar-shaped thing. Later estimates, I think most people now would be a bit more restrained. They would now say it's more pancake than cigar, maybe 6 times as long as it is wide. But you've still got this elongated structure tumbling through the solar system. Why is it tumbling? Not sure. Maybe a violent start wherever it came from. Something flicked it into galactic space. We're not sure. But that explains the change of brightness. And before you stare too long at this artist's impression, I want to remind you that this is the best image that we've got, right? Not this or this, this. We're talking about the real stuff. But we think it might have looked like this. So, we can imagine, but we must always remain grounded in reality. There were 2 other odd things about this object. So the color, unusual but not that unusual. The shape, pretty unusual compared to the asteroids that we've studied in the solar system. There were 2 other unusual things. One is that trajectory where it came in originally seemed to be close to something called the local standard of rest. What that means is it seemed, before it encountered the solar system, to be moving along with the nearest stars to us. So, is that unusual? Don't know. We've only seen one of these things, but if you were going to throw these things randomly around the galaxy, you wouldn't expect it to be following the nearby stars. So maybe it comes from one of those nearby stars. And then the real mystery is that as we watched it recede from the solar system, we're expecting it to slow down because of the gravity of the sun. Leaving the solar system takes energy. You have to climb out of the sun's gravity well and escape. Oumuamua did slow down a bit, but much less than we thought. There was some accelerating force pushing it out of the solar system. This would make sense if it was a comet. We've seen comets. This is the close-up nucleus of Churyumov-Gerasimenko, which was visited by, I mostly put it in so I could say Churyumov-Gerasimenko, because once you've learned to do that, you use that skill as often as possible. It's like trying to pronounce the Icelandic volcano that caused the dust storm more than a decade ago, Asteroid, if you were asking. Anyway, Churyumov-Gerasimenko, the other Churyumov-Gerasimenko story is that it was nicknamed Chewy Gooey by the scientists who built the probe that went there until they worked out that both Churyumov and Gerasimenko were still around and would prefer not to have their discovery shortened. So we can call it 67P. This is the comet we know best. Rosetta spent more than a year in orbit around it. And as you can see, this is it in active phase. And there's this jet of material shooting out. So comets, which are made of ice, don't melt evenly when they come into the inner solar system. You get these dramatic jets, and so that will have a rocket effect pushing this thing in this image up. And so if Oumuamua was only a comet, then this acceleration would make no sense. But it's only a point of light. How do we explain this acceleration? So we have a first visitor to the solar system. We don't know where it came from, but we know it came from somewhere else. It appeared unannounced. It moved through the solar system silently. We know, we checked, we pointed radio telescopes at it just in case there were signals being sent. There weren't, or at least none that we could hear. But now it's speeding up as it leaves, almost as if it's fired its engines. And all of these thoughts combined with the fact that Arthur C. Clarke wrote a book called Rendezvous with Rama back 50 years or so ago, which describes the visit to the solar system of a mysterious, long, cylindrical object which passes silently through the solar system. And despite, in the book, people going to visit it and exploring it inside, and it's obviously artificial, it remains mysterious and disappears off into the rest of the galaxy, firing its engines as it goes. So, this idea that maybe this is exactly the behavior that one would expect from an alien spacecraft was something that occurred to lots of us at the time. It also occurred to a Harvard astronomer called Avi Loeb, who believes very seriously that this is clearly an alien spacecraft, and has written a 250-page book explaining why the rest of us are too stupid to agree with him. But it's a serious scientific point. We have an unusual set of properties. Should we consider an alien spacecraft as a possibility? It's so tempting to say yes and leave. But actually, I think there are good explanations for the unusual things that we know about Oumuamua. So I'm going to tell you about them, and then I'm going to try and convince you that it's interesting anyway. The trouble with mentioning aliens is that people always want it to be aliens. I tried to write a book called It's Never Aliens, which was going to be a story about all the things that turn out not to be. And I got a one-line review from a potential publisher that just said, but we wish it was. Which is fair, but this is still an exciting object. But let's deal with the unusual things. Firstly, the shape, this elongated shape and its color. Well, if you talk to people who study the small bodies of the solar system, people like my friend Michelle Bannister, they'll tell you that the most unusual thing about this object is that we've studied it in this detail at all. If you ask the people who control the Very Large Telescope to look at a random asteroid that's only 200 meters across, of which there are millions and perhaps billions in the solar system, they're going to tell you they've got better things to do looking at Jupiter and distant galaxies and planets around other stars and all the other things that we're doing as astrophysicists. So if you took it and put it amongst its peers in the solar system, it may not appear that unusual in shape or color. The fact that it's close to the local standard of rest, that it's moving with the stars, it turns out it's not that close, and that you could have got that alignment by luck. And then there's this acceleration, this fact that it fired its engines or sped up as it left the solar system. Well, we think we've got a couple of explanations for that as well. One is that things are changed by time in space. Next time you get a chance to look at the full moon, you'll see the familiar seas, the dark areas, which are lava, and then the brighter areas on the moon, which are the highlands. And on the whole, those are older areas. But where a crater has punched into the surface, for example, the large crater at the bottom of this image here, you can see, I hope, that there are bright rays of material that shoot out across the surface. And they're bright because they're fresh. They're material that's been dug up from underneath the surface and distributed across a large percentage of the lunar surface. They're now exposed to particles called cosmic rays, which come from the sun, but also come from the galactic environment. And these high-energy particles hit the surface of the moon all the time. We're protected down here on Earth, for the most part, by our magnetic field. But on the moon, the surface is exposed to these cosmic rays, and over time, over millions of years, they will darken. Now, Oumuamua must have been exposed to cosmic rays as it traveled through the galaxy, perhaps for billions of years before it reached us. They would have had the effect of exciting and getting rid of water or other volatiles, carbon monoxide, carbon dioxide, from the outer layer. And so you end up with an object which is an icy core with a crispy crust around it, a kind of celestial magnum, if you like, without the stick, obviously. There's a marketing opportunity in there somewhere. They will tell the Gresham that we need our own ice creams. Anyway, so this is the idea. So it's a hidden comet. And so when it comes into the solar system and warms up, you may get less activity than expected, but you may still get these jets. And so we wouldn't have seen the activity, because it wasn't dramatic enough for even our largest telescopes, but you can get this accelerating effect. Or, if you don't like that idea, we have others. There's a group of astronomers led by Darrell Segelman who have published papers like this one that claim that perhaps it was made of hydrogen. So perhaps it was a hydrogen iceberg that formed somewhere like the Orion Nebula in one of these dark star-forming nurseries, and has traveled through the galaxy. And the point here is that you can heat hydrogen up and you would have got these jets of material without us being able to detect it. So you can sort of sneak your way in this way. Personally, I think dehydrated comet, icy shell, crispy shell, and icy center is the way to go, but there are other arguments. And that's all we know about Oumuamua. It's very satisfying, this lecture, because we will never know anything else about this object. We can't go and chase it. It's gone too quickly and too far. It's lost to our telescopes. And very soon, we won't even have the accuracy to go and chase it, even if we wanted to in the future. If we invent, I don't know, the Lintott drive that can go close to the speed of light, we won't know where it is. Interesting, though, and I think probably luckily for all of our sanity when we're arguing about whether this first interstellar visitor really is an alien spacecraft or not, we have been visited by a second interloper. This is a Hubble Space Telescope image of an object called Comet Borisov, which was discovered in August 2019 by a remarkable astronomer. Borisov is a technician at a large observatory in Kazakhstan, I believe. But in his spare time, he's an astrophotographer. And so not during his day job, but in his night job, I guess, as an imager of the skies, he discovered this comet, which turned out to be on a similar trajectory to Oumuamua. It's come from outside the solar system. It traveled through the solar system. This image is taken when it's about 300 million kilometers away. And I should say the thing on the left here, that's a galaxy. It just happens to be in the background. But the blue thing is a comet. As you can see, it's got a tail. It's behaving much more like a normal comet. So we know that we can get normal interstellar objects as well. Borisov is exactly what was predicted. It had an interesting encounter with the solar system over time. These are images of the nucleus, the center of the comet, and you can see on March the 28th, it seemed to split up into two pieces a few hundred kilometers apart. This is typical of comets that get too close to the sun and break up. And so we have an icy visitor from another solar system. And if you think about the geometry of the solar system that I showed you earlier, which has that Oort cloud, that reservoir of comets in the outer solar system, it makes sense that interstellar objects would be comety, because it's easier to escape the sun's pull if you're already a third of the way to the nearest star than it is if you're all the way down here in the inner solar system at the bottom of the gravity well. So rocky asteroids, which tend to be found near the sun, won't have escaped. Perhaps lots of these comets on the outskirts do. So we now have two of these things. I was convinced that this morning was going to see the announcement of a third one, but no, so far we're still waiting 5 years on from our second interstellar object. But actually there are clues in our solar system that suggest that these things are very common indeed. And the first set of clues, the most important ones, come from that outer edge of the solar system where Pluto lives. Pluto, of course, definitely not a planet, as I've mentioned in all of my lectures so far, much to the distress of at least 3 people online. But it's not a planet because it's not interesting. Like, we didn't decide it was boring. In fact, this image from the New Horizons probe, which flew past it in 2014, showed that it was much more interesting than we thought. It's a world with some differentiation. It has this heart-shaped plain of water ice, now known as Sputnik Planeta. It actually has mountains of water ice, frozen solid. It has these dark patches, actually rather similar to the color of Oumuamua. And it has a complex interaction with its large moon, Charon. But it is only one of many millions of objects that live in the Kuiper belt, our solar system's outer asteroid belt, this region where planet formation, this process of adding grains together to form boulders, and boulders together to form somehow skyscrapers, and skyscrapers together to form planetesimals and then onto planets, didn't proceed as far as it did. Out in the Kuiper belt, what we have is the rubble of a failed construction project. There wasn't enough time to build a planet before the sun got going and heated up the disk and expelled most of it. And the denizens of the Kuiper belt are interesting in many ways. New Horizons, when it went past Pluto, headed off through the Kuiper belt, and the team looked for another object that they can visit. They actually used the Hubble Space Telescope to look in the direction that their probe was going and tried to discover an object to order, something close enough that they could divert to. And they found it in a small world called Arrokoth, which is only a few hundred meters across. This is the closest color image we had of it from that flyby. It flew by on New Year's Day 2019. From a distance, it looked beautifully like a champagne bottle, which was great. As we got closer, it's much more snowman-like. But the key thing here is that this is not really one object, it's two that have collided. You can see there's a bright ring between the two spheres, between the snowman's head and body. And that's where these two objects have gently drifted into each other and stuck together. They're icy. It's slushy when you combine the two things. And so this is a double object. And in fact, lots of the worlds that we know of in the Kuiper Belt are binary rather than solitary. Pluto even has its moon, Charon, which is much closer in mass and size to Pluto than any of the major planets. The next one down is the Earth moon, but Pluto and Charon are much closer. Big things like Eris, another of the large Kuiper Belt objects, are double. Many of the small worlds seem to be. And of course, the comets, like 67P, Churyumov, Gerasimenko, that live out there, this could well be a double object as well. It looks a lot like Arrokoth. And so somehow we've formed these binary or double worlds. And the best explanation for that is that the Kuiper Belt was once 1,000 times denser than it is today. Instead of having a few % of the total mass of the Earth spread out amongst these bodies, we might have had 6 or 7 Earth mass worth of stuff out in the solar system. So where did it go? Well, we have a theory for that as well. We have to abandon the idea that our solar system is a nice, stable place. This is a simulation of the first billion years of our solar system's history, and we're looking here at the outer solar system. So the rings are the orbit of the 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, and the green things are the Kuiper Belt objects that are left over. So if I run this, the time is in the top in millions of years. The first billion years, few hundred million years, nothing happens. Everything's nice and stable. You can see the planets are moving about very slightly. That's because of their mutual gravitational attraction. Jupiter's pulling on Saturn. Saturn, Uranus, and Neptune have a collective effect on Jupiter. Uranus and Neptune interact. But nothing really happens for 600, 700 million years. But in this simulation, when we reach about 800 million years, and we'll slow it down, a resonance is achieved. Saturn and Jupiter start lining up, and all hell breaks loose. So what happens is Jupiter and Saturn get themselves into a pattern where they line up in the same part of their orbit every few orbits, and that gives a regular kick to the rest of the solar system. So it's like if you're pushing somebody on a swing, if you always push at the same point, you get a much better response from the swing. That causes havoc in the outer solar system. Jupiter tends to move inwards, Saturn tends to move outwards. Uranus and Neptune swapped places. I don't know if anyone noticed that in the animation. And the Kuiper Belt is scattered out into the galaxy. And so what we see in our Kuiper Belt, Pluto and friends, are the survivors of this most dramatic event. We think that our solar system donated 10 to the 16. So what's that? That's something like, let's say, 100 million billion objects to the galaxy. And if every other solar system does that, objects like Oumuamua are the most common macroscopic objects, the most common things in the galaxy. There are billions and billions and billions of them out there. They're passing through our solar system all the time. Calculations show, with a large error bar, that there's almost always something the size of Oumuamua within the orbit of Neptune. We're just extraordinarily bad at spotting them because they're small, they're dark, and they move fast. And so we shouldn't really be surprised that we saw Oumuamua. We should be surprised that we've only found 2 of these things. And this is the answer to the mystery that I left open at the start of the talk. How do we jump from things that are boulder-sized to skyscraper-sized? Well, Oumuamua, a few hundred meters across, is a flying skyscraper. That disk of material around the young star will be peppered with these interstellar objects flying through from other solar systems. And Suzanne Felstner and Michelle Bannister have proposed the idea that the seeds of planet formation come from these interstellar objects. Get started quick way of building a solar system the equivalent of a ready meal, I guess. If you start with the disk capturing these objects, then you can quickly grow a planet. All right, you have to form planets somewhere the slow way. Somebody has to do it the hard way. Somewhere in the dim, distant past of the Milky Way, there was a star with a long-lived disk that could have formed planets, which would then have scattered 10 to the 16 interstellar objects. Those would have kick-started more planet formation. And suddenly you have this runaway process that spreads very quickly through the galaxy and allows us to form planets rapidly and makes it so that we live in a universe where planets are common and there are worlds to explore. So though Oumuamua isn't, I promise, it's not an alien spacecraft. There's too many of the things, and the fact we found 2 and we'll find more tells us that. It still, I think, has a message for us, which is that what's happened here, that in explaining our solar system, we've got no choice but to consider ourselves as part of a galaxy connected by these scouts, these messengers that wander between the stars. Thank you very much. And now, buy my book.
Chris, thank you very much, and let's all just take a moment.
Oumuamua is on there, you see, it's on the cover, so it is relevant in the blue.
Fantastic. Well, wow. Well, we've had it all. We've had a world that's not a planet, but it's sort of like one of those things like if it looks like a planet and it smells like a planet, why is it not a planet?
Small.
Okay, it's too small.
We're going to keep coming back to Pluto.
I'll move on.
I promise to get it into every talk now.
Excellent. And then we've also had a flying magnum. That was a highlight. So loads and loads to talk about. Lots of questions. And I think actually, right, okay, let's just hit the alien issue right now, because I'm not going to lie to you, Chris, that is a feature in quite a lot.
Hello, the internet.
Of these questions. So just to pick up on that last point you made, and I think sort of collect some of these questions together. So obviously there's a degree to which, some in humour, some not so in humour, there's a disappointment. This isn't an alien, this isn't Arthur Clarke's vision, this isn't a spaceship. But actually, I thought it was really interesting how you said, well, if we can get past some of our expectations, not just about what we should be looking for, what we should be seeing, or what we would like to see, but actually it's really exciting to, like, the implications of something like this could actually be really enormous for how we consider the universe. Is that about right?
That's right. And I think one of the things Oumuamua taught me, and I've changed what I'm working on to pay attention to things like this, is that we should be ready to be surprised by the universe. This is our solar system, right? We've lived in it for a while. We've sent probes into it. We've mapped it. Yes, all right. We find new asteroids daily. There's a catalogue of a few million of them. This is our backyard. And yet, Oumuamua tells us that we can be caught unawares, that the unexpected can still happen, that actually, in the solar system, there may be types of object we haven't thought of yet. There may be a population of hidden comets in the distant solar system. There may be things in unusual orbits. There may be an alien spacecraft lurking between Mars and Jupiter that we haven't found yet. We don't know. And so, particularly, I'm working on this thing. This is the Vera Rubin Observatory. This is going to do a new survey of the sky, which will find in its first year, we think, 6 million asteroids. And one response to that is to say, great, we've got lots more asteroids. The other is to say, okay, which 10 of those are most unusual? And what are their properties, and what do they tell us? Now, my guess is that they'll tell us about details of how the solar system formed and how it perhaps has evolved in the 4 billion years. But we should consider the possibility of looking for what are called techno-signatures, so spacecraft in there as well. But we can do that by looking for weird astronomical things. And only when we've ruled out an astronomical origin, then I'll turn around and say, okay, maybe. But for Oumuamua, there's no evidence it's anything other than a really fascinating astronomical object.
Great. So you're not taking aliens away from they're not off the table completely.
Nope.
They're just slightly to the side. And if
they shouldn't be your first. I mean, I think where I disagree. So Avi Loeb, who is the advocate of these things, would say that they should be the first thing we think of. That when we see something unusual, we should say, "Is this aliens?" before we do anything else. And that's fine. But it doesn't really get me very far. Because the answer is always maybe. What I have to do is see if there's another alternative explanation first, and then get driven to the more extreme or more unusual claims at the end.
Great. So if we maybe challenge some of our expectations or maybe aspirations, then we might be able to ask different kinds of questions, which are always really interesting for science. So let's take a question from the floor.
A couple of observations. Those two objects, 1I and 2I, remain unique. Of course, when the Vera Rubin telescope starts operating, then we may find a lot. If we don't, and in particular in the case of the more mysterious one, which is 1I, Oumuamua, then given that it is, and I'm told this by people who understand these things, it is in principle possible to send a mission to it. Should we do so?
Yeah, so a few questions there. So with the Rubin telescope, we think we're going to find about 100 of these interstellar objects, but that number could be 10 or it could be 1,000. It depends slightly on how optimistic we're feeling, because we're trying to extrapolate from 2. I should say I've got a PhD student, Matthew Hopkins, who's been working on this, and we can predict what these things will be like based on what we know about the galaxy. And we think that even if we find 50 of them, Oumuamua may still look odd, because it is on the extreme. It's not unusual. It's unusual, but it's not a complete outlier. So we shouldn't be surprised if the first 10 that we find all look like Borisov. They look like comets. We think we'll find a population of Oumuamua-like things. But we don't know, so we'll have to find out. There's also a NASA mission that's, again, looking for near-Earth asteroids that will launch in 2028, which will find lots of these things. So in 10 years' time, we should have a few hundred, and then we can say something sensible. Should we launch a mission to Oumuamua? If we could, I definitely would. It'd be fascinating. There are all sorts of questions about it, as you've seen. For a sensible budget and a sensible timescale, I don't think we can get there in time, because the problem is we only watched it for a few months, and so the error on its trajectory is large. And so I think we're close to the point now that even if you had all the money in the world and you could launch with our best rocket a satellite right now, you wouldn't necessarily find it, even if you could hit the speed. So I think it's gone, sadly.
I think that's true. Well, I would suggest you look at something called Project Orion.
Yeah, I know about. Yeah, I love their optimism.
I'm going to take one more question.
Should say, by the way, we're going to do another episode of the Gresham podcast. Any questions? So we can answer more questions. So do send them in, and I promise I'll get to them. Yeah.
What are the chances of New Horizon finding further objects, and would we find out important things if it did?
Yeah, it's a good question. So the New Horizons team spent a lot of time using Hubble looking for a third object that they can go to. They don't have much fuel left on board, so they can't really divert. So they need to find something in the direct line, and they've more or less given up on that. What they're doing instead is it does have a telescope on board, so it's doing observations of relatively nearby Kuiper objects. After all, it's much closer to them than we are. And so we're actually building up a library of images taken from quite a long distance, but much less than we have of these objects. So it's sort of become an astronomy satellite. It's also monitoring the effect of the sun on the outer solar system. So it's still doing science, but I don't think we'll get another flyby like we did with Arrokoth unless we get really lucky.
Okay, great. Well, thank you so much. There's lots and lots of questions. Unfortunately, we're out of time, but as Chris has just kindly volunteered to do another Any Further Questions podcast, look out for that, and I'm sure if your question's on here, he'll get to it, even if it is about aliens.
It's still not aliens. I'm sorry.
Chris Lintott, everyone.